This is episode 4, Magic of Primes under Mathematics Universe. In the last 3 episodes, we have been concentrating on checking prime numbers. We have already seen 3 different techniques. And in the first technique, we were taking all the numbers right from 2 to n minus 1 and we were checking. In the second approach, we were checking between 2 to n divided by 2. In our last approach, we were checking from 2 to square root of n. And in this episode, we will try optimizing it much better. So to see the new optimized procedure, let's take some example. And the example that I would want to take is n is equal to 901. If n is equal to 901, what is the last approach, optimized approach that we have seen? Checking between 2 to square root of n. Here n is 901, then what is the value of square root of 901? Square root of 901 is approximately 30. So which means we need to check between 2 to 30 basically. So let's just list out all the values right from 2 to 30. So we have taken values right from 2 to 30, which is 2 to square root of 901. And now what is the procedure? Step 1. Let's check whether 901 is divisible by 2. Is it 901 divisible by 2? No, it is not. Now the question is, if 901 is not divisible by 2, if any number, if it is not divisible by 2, will it be divisible by 4? Will it be divisible by 6? Will it be divisible by 8? Will it be divisible by any of the multiple of 2? No, it will not be. If a number is not divisible by 2, it will not be divisible by any of the multiple of 2. Simple max. So which means if 901 is not divisible by 2, it is an indirect statement that it is not divisible by 4, it will not be divisible by 4, it will not be divisible by 6, it will not be divisible by 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We need not to check all these numbers, 4, 6, 8, we need not to check and waste. We need not to check and waste. Okay, similarly, we will proceed further. What is the next value we have? 3. Is it 901 divisible by 3? No, it is not. So if a number is not divisible by 3, then the number will not be divisible by any of the multiple of 3. So which means it will not be divisible by 6, it will not be divisible by 9, it will not be divisible by 12, then not 15, not 18, not 21, not 24, not 27, not 30. It will not be divisible by any of the multiple of 3. Then let's take the next value. 4 we need not to check because already it is indirectly understood. Because the number is not divisible by 2, it will not be divisible by 4. Do not check with 4 and do not waste the time. Let's directly jump to 5. Now I'm going to check 901 whether it is divisible by 5. It is not. When 901 is not divisible by 5, it will not be divisible by any of the multiple of 5. So once if you checked with 5 and it is not divisible, then do not check with 10, do not check with 15, do not check with 20, do not check with 25, do not check with 30. This is our idea. If you check with 2 and if the number is divisible by 2, it is not a prime number. You will stop the process. But if the number is not divisible by 2, don't check 4, 6, 8. Do not check and waste the time. Remove all the multiples of 2. Leave them out. And then if you check whether the number is divisible by 3, then stop and say it is not a prime number. But if it is not divisible by 3, then leave all the multiples of 3 out. Do not check them. This is our core idea. So now, similarly, we have to proceed, but let me circle the numbers which have not been striked out, which has not been eliminated. So like 7, 11, 13, 17, 19, 23, 29. I've just circled all the values which have not been eliminated. And just if you look at all the circled values, we can observe something. These circled values are generally called as prime numbers. They're all called as prime numbers. So which means, what is our understanding? The understanding is that we need not to check all the values from 2 to square root of n. We need not to check all the values right from 2 to square root of n. No need of checking all values. Just check only the prime numbers between that range. So if you want to check whether n is a prime number or not, then just pick all the prime numbers between 2 to square root of n. Just pick all the prime numbers between 2 to square root of n and then check. Do not check all the values between 2 to square root of n. This is how we are going to optimize. But there is another question. How are we going to get all these prime numbers? Between 2 to square root of n, we need all the prime numbers. How are we going to get it? Are we going to generate it? If you have to generate it, it will take too much of time. Rather than generating, it is better to take all the values from 2 to square root of n. Then what we are going to do to get those prime numbers between 2 to square root of n? So here is where I want to speak about a very interesting property. Every prime number except 2 and 3, every prime number is of the form 6 multiplied by k plus or minus 1. If you pick any prime number apart from 2 and 3, every prime number is of the form 6 multiplied by k plus or minus 1. Let's take some example and understand. I will just make this into two different equations. One is going to be 6 multiplied by k minus 1 and one is going to be 6 multiplied by k plus 1. And now I will start taking the value k is equal to 1. K minimum value for k is 1. And we will take k is equal to 2, k is equal to 3, k is equal to 4. Now, what if k is equal to 1? Then 6 multiplied by 1, 6 minus 1 is going to be 5, which is a prime number. Then 6 plus 1, 7, which is also a prime number. Then k equal to 2. 6 multiplied by 2, 12, 12 minus 1, 11, which is a prime number. Then 12 plus 1, 13, which is also a prime number. 6 multiplied by 3, 18 minus 1, 17 is a prime number. Then 18 plus 1, 19 is also a prime number. Then again k equal to 4. 4 multiplied by 6 is 24. Minus 1, 23 is a prime number. So 6 multiplied by 4, 24 plus 1, 25, which is not a prime number. So that's exactly the point is, every prime number apart from 2 and 3, every prime number is of the form 6k plus or minus 1. But not all 6k plus or minus 1 are prime numbers. That is our point. Every prime number is of the form 6k plus or minus 1, but not all 6k plus or minus 1 are prime number. So when we start taking all 6k plus or minus 1, definitely all the prime numbers will be covered, but along with that few non-prime numbers will also be covered. No issues. Now see, the concept is, instead of taking all the values right from 2 to square root of n, can we just pick just simply 6k plus or minus 1 values? All the values which are in the form of 6k plus or minus 1 between this range, just taking them will cover all the prime numbers. Maybe 1 or 2 non-prime numbers also will be covered. That is not an issue. But you look at this concept here, we have not taken 6. We have completely ignored 6. Then we have ignored 8, 9, 10. Then we have ignored 12. Then we have ignored 14, 15, 16. We have ignored 18. Then 20, 21, 22. Then we have ignored 24. Then several other numbers. See, literally more than half of the values we are not taking. We are not picking, which is a clear optimization. So the concept that I want to propose here is, the idea is, instead of taking all the values right from 2 to square root of n, I suggest to only consider the values which are in the form of 6k plus or minus 1. Just take these values. And remember, this does not include 2 and 3. So apart from 6k plus or minus 1 values, you also have to take 2 and 3 separately, manually. And how to take this 6k plus or minus 1? And if you notice here, there is a clear pattern. See, let us assume that I will start taking I and that I begins from 5. Let us start that our loop starts with 5, I equal to 5. And if this is 5, then what we can, if 5 is taken as I, if considered as I, then what we can call 7 is. If 5 is represented as I, then 7 can be represented as I plus 2 generally. Then you see here, the I value is changing to 11, which is literally plus 6. 5 plus 6, 11. 5 plus 6, 11. Then if you see the other side, 11 plus 2, 11 plus 2, 13. Then 11 plus 6, 17. Then 17 plus 2, 19. Then 17 plus 6, 23. Then 23 plus 2 is 25. And what is that we are able to see? If this is I, then this is I plus 2. So if we have I, we can take this I plus 2. So where the I value starts from 5 and it keeps incrementing by 6 every time. And whenever we are picking I, we also should be picking I plus 2. Right? So how our loop should be actually. How our loop should be for integer I equal to 5, because that's where this formula starts. 5 is where the formula starts. And every time I is incremented by 6. Every time it is incremented by 6. So I think I'll leave the condition part out. But in the incrementation, I can write I is equal to I plus 6. And what about the condition? If we keep incrementing it by 6, when we should be stopping? See, we're saying that we have to pick all the prime numbers between 2 to square root of n. What does this prime numbers mean? 6k plus or minus 1. So we have to be picking all 6k plus or minus 1 within square root of n, which means the loop should not cross square root of n, that is I less than or equal to square root of n. Hope we have seen this condition priorly and we dealt this little differently, right? So squaring on both sides, the left side become I multiplied by I and less than or equal to, the right side becomes n. So let us replace this condition here, I multiplied by I less than or equal to n. So the loop will not cross square root of n. Now what is that we need to check within this loop? And if you see here, if 5 is taken as I, 7 is I plus 2. If 11 is taken as I, 13 is I plus 2. If 17 is taken as I, then 19 is I plus 2. So when you get inside, you have to check either your input is divisible by I or otherwise it is divisible by I plus 2. Just check both of them. If it is divisible by any one of them, if it is divisible by I, then stop and say it is not a prime number. If it is divisible by I plus 2 also, just stop and say it is not a prime number. So if this condition is true, we will just simply return false. But if this within this loop, if this condition is not at all satisfied for once, if it is not at all satisfied for once, then the number has to be a prime number. So once you come out of the loop, we have to return true. And there is one more thing. This formula starts from 5. This formula does not check 2 and 3. This formula does not check 2 and 3. So what we have to do? Above the loop, we have to separately check if the input is 2, if the input is 3, they are directly prime numbers. Let us not check. because if the input is 2 or 3, they will be divisible by 2 and 3. So we have to check whether the input n is greater than or equal to 4. If the input is greater than or equal to 4, then we will check whether it is divisible by 2 or it is divisible by 3. Whether it is divisible by 2 or divisible by 3. If it is either divisible by 2 or divisible by 3, there we will stop and just simply return false. Why are we checking this 2 and 3 separately? Because the formula starts from 5 and the formula does not include 2 and 3. Right? And in the previous approaches, we also had one more condition, that is if n is less than or less than 2, we will also directly return false. That's it. This is how the implementation will look like. And let's just jump into the implementation. We'll get to the IDE. As per the concept that we have discussed now, let's start implementing. And we have the solution that we had in the previous episode, and there are a few changes to it. And the number one change is that before the loop, we have to just check whether if the input is greater than, num is greater than or equal to 4, and at the same time num is divisible by 2 or divisible by 3. And suppose if the input number is divisible by 2 or divisible by 3, then we can confirm that it is not a prime number and we can just simply return false. Then coming to the loop should not be starting from 2, the loop should be starting from 5, it should be starting from 6k minus 1, 6k plus or minus 1, right? That formula starts from 5, we have to start there. And the condition does not change, condition is same. This says that I is less than or equal to square root of num. But coming to the incrementation part, it is not going to be I plus plus, it is going to be I is equal to I plus 6. Hope we have discussed this priorly, that every time I is incremented by 6. Now going inside, we will not just check I, we will also have to check whether the num is divisible by I plus 2. So is it num modulus I equal to 0, or otherwise num modulus I plus 2. Is it num divisible by I plus 2. So num modulus I plus 2 equal to 0. In that case also we will return false. And finally, suppose if we are surpassing the loop, then it's a clear indication that the given number is a prime number, so we will return true. So first, if condition num less than 2, we are trying to prove that the number is not a prime. Then second condition is also we are trying to prove the number is not a prime. The entire loop also we are trying to prove that the number is not prime. Surpassing that, we have tried all ways of proving the number is not a prime, but we failed. That's the reason why we reached the 14th line, crossing all the return statement. So when we reach 14th line, we can very confirmly say that the input number is a prime number, so we are returning true there. And with that, let me start with just compiling this. And there is no syntactical error, and let's just execute it. And first we'll go with 1, it's not a prime. 2, it's a prime number, exactly. 3 is a prime number. 4 is not a prime. 5 is a prime number. 6 is not a prime. 7 is a prime. 8 is not a prime. 9 is not a prime. 10 is not a prime. 11 is a prime. Then 12 is not a prime. Then 13 is a prime, and so on. So this works absolutely fine, and this is the ultimate, the most efficient approach that we have for checking whether the given number is prime or not.